Hi, my name's David Veitch. I'm one of the PhD students at the UCL-Energy Institute, and my project is looking at developing improved methods for measurement of ventilation rates in houses. So ventilation in buildings is important in relation to indoor air quality, which is related to occupant health and comfort. However, in the UK housing stock, it's accounts for about 20% of the heat loss. So in efforts to reduce this energy consumption, we're sealing up buildings tighter and tighter. But as we do that, it becomes even more important that the ventilation systems that we do install, that they operate effectively. So to check this, we should really be looking at what's happening in reality. So looking for evidence of people going out and measuring ventilation rates, there isn't really very much of that data around, and that's because ventilation is pretty tricky to measure. And the data that is around typically shows that the ventilation systems fail to deliver what was anticipated. So from that, the techniques to measure ventilation, the only way to directly infer the rate, use tracer gases. And although these methods have been around for maybe 20, 30 years, a lot of them require quite specialist chemicals, technology, or they're quite limited in the results that they give. So my project is really looking at how can we leverage developments in technology, chemistry, sensors, etc., to improve these methods. So following a literature review, I discovered a technique that borrowed from other areas of engineering, which used a system identification approach. And basically the way these techniques work is if you have a system, which in this case is a building, simplified here with lots of airflow between all the rooms, you introduce a signal to disturb the system, and this is a tracer gas. So you introduce signals of tracer gas into all the different parts of the dwelling, and then you monitor the response of the system, in this case which is the concentrations of the gas. You can then correlate the inputs and outputs, and that effectively gives you what's called the impulse responses of the system, and then basically you can solve these outputs to derive the airflow rates not only from the external of the building to the inside, but also between all the zones within the building. So the benefits of this technique, if it all works, is that it gives you not only an estimation for the building as a whole to the ventilation rate, but it also allows you to look at the spatial distribution, which might be of interest for pollution dispersal. And also it allows you to look at the temporal distribution, so you can see potentially when occupants take action to control the ventilation rate. The technique also doesn't require precisely calibrated equipment, and also doesn't need to know how the release rate of the tracer gas, so it allows use of quite simple equipment. And also again, the technique, because it's correlating inputs and outputs, it is quite robust to excluding noise from other sources. So for example, for my technique I'm looking to use carbon dioxide as a tracer gas, even though that there is occupants inside which give out carbon dioxide. So the stages of the project started with doing lots of modelling and exploring the theoretical performance of the technique. So that was looking at what kind of equipment did you need to carry it out, what happened under varying flow rates, and things like this, and that was reasonably encouraging. So I moved on to the next stage, which is crossing over to the physical domain. So I'm carrying out tests in a very controlled physical environment, which is a large box with lots of fans, computer controlled to simulate different ventilation patterns. And then following this, hopefully, I'm going to move on to do some brief case studies in actual houses that are occupied. And here I'm looking to compare the results of this new technique to more tried and tested methods and to see how it holds up. So I'm currently in stage 2, but hopefully get here before the end of the year. Thank you.